So we've been talking about pure substances and their phase diagrams. So we've got the PV phase diagram, pressure volume. We saw liquefaction. We saw solidification, so solid, liquid, gas. We had those. Then we looked at the PT phase diagram, kind of rotating at 90 degrees and looking at that plane. And that's all fun. You finally kind of feel like you understand phase diagrams. And then I twisted a little more. Okay, so today's the twist. All right, we're going to leave one component phase diagrams behind. And so for the rest of this middle section of phase diagrams, we're dealing with X, the mole fraction. And so now we have a fourth variable, which really messes things up because we cannot plot, with a single component, we could have pressure, temperature, and volume. Those are our three variables. But now we add more than one component, so we have a fourth variable. So there's no real way to visualize this in multiple dimensions. So we're going to go back to just two-dimensional graphs, and the x-axis is always going to be composition. So on one end we'll have a pure substance A, and the other side a pure substance B. So this x-axis is mole fraction. So right in the middle is 50-50, and 60-40 and all of that. So, and then the vertical axis will be some state variable. So we'll go with pressure and temperature. We'll cover those two. So today we're just looking at pressures of mixtures. And so they're called PX. X is the mole fraction, the mixture. So these are PX diagrams that we're talking about today. And then we'll look at ideal and real solutions. Like, does the pressure always just the ratio of whatever component is in the solution? And it's not really. So we'll see. So we get into mixing now. We talked about the enthalpy of formation, and it was the pure unmixed reactants, or enthalpy of reaction. It was the pure unmixed reactants reacting and giving us pure unmixed products. And if it's an ideal solution, there's really no enthalpy change when you mix them. But we're dealing with real mixtures now. So this is the enthalpy of mixing. And so if it's ideal, there's no intermolecular attraction differences on mixing. So that's, unrealistic to say that there's no intermolecular attractions because you have liquids. They wouldn't liquefy. Remember our ideal gas, right? So they would not liquefy if they didn't have intermolecular attractions. But this is saying there's no real difference in the products mixing versus the reactants mixing. And that could be legit, right? If you have some, I don't know, you've got an alcohol and an acid group reacting to make an ester or something like that. They're both starting, the reactants are polar, some hydrogen bonding. The products are polar, have some hydrogen bonding. And so there may not be a huge difference in the solution before and after the reaction. So that reaction enthalpy may be pretty close to the standard reaction enthalpy that you would calculate from the tables. Okay. And so if it's an ideal mixture, there's no difference in attraction between reactants and products, or between taking those, sort of hypothetically separating them as reactants, mixing them or reacting them, and then mixing them back together as products. Or you could calculate it if you know something about the intermolecular attractions. And so I put the word Hansen here because we can use the Hansen solubility parameters to calculate this delta H of mixing. There's a whole lab where you determine the Hansen solubility parameters. So when we get back from spring break, there's no lab. I kind of give you guys a break on that. Also to kind of serve as a safety valve in case we had another February storm, snowpocalypse. And so we didn't have to use that. So you guys get a break when you come back. So those Monday folks aren't going to have to get ready, during spring break when you come back. So we won't have lab that week. But then the next week will be the Hansen solubility parameters lab. For that, you need to bring a piece of plastic that's about, in terms of surface area, about 3 inches square of surface area. It doesn't have to be a flat piece of plastic. It could be a 3D printed part or whatever, but you just need to have a place to put 20 drops. And so we'll take that plastic and we'll put 20 different solvents on it and see how the solvents attack that plastic surface. Yeah.
Any specific type of plastic? Because as you there's all different types.
Yeah, that's the beauty of it. So whatever type of plastic you want to bring in. Yeah.
So
And
will the plastic be destroyed?
it's going to be messed up, yeah. Yeah, that's right. So if it's something you like really value, so don't do
I
that.
don't want to be like Tupperware. I was going to bring Tupperware.
No, but that'd be fine. Yeah, yeah. If you have a spare. Yeah. Yeah. Yeah, that's right. So go get some of the sandwich meat that's in the little, cheapo ones. Yeah. And so then, and that lid of like the lunch meat lid, that would be perfect. Something like that. You don't all have to have different ones. If y'all have similar ones, that's fine. So what you'll do is you'll expose that to 20 different solvents, and some solvents will interact with it strongly. Like it'll cause it to change color. It may get sucked into the plastic. That would be a really strong interaction. That means the Hansen solubility parameters for the plastic and the solvent are very similar. Like dissolves like, okay? And then there'll be lots of solvents that don't do anything. They beat up. You put a drop on there and they make a little, they don't wet the surface. And so that would be no interaction. And their Hansen solubilities are going to be dramatically different. And then we'll go into Excel and we'll analyze the properties of that plastic. And it'll sort of put this plastic in terms of what we call the dispersion, polarity, and hydrogen bonding forces. So we'll get into all of that when we come back from spring break. Okay, so that's not the very next week, but the week after that. But if we know those Hansen solubility parameters and you can add them together to make a total solubility parameter. This is saying if there's a big difference between those two solvents. So this is the total solubility parameter for substance 1, the total solubility parameter for substance 2. The difference between those squared is going to be giving us a high or a large enthalpy of mixing. So that's a barrier to mixing, and we get phase separation. So when things don't mix, this is one of the ways to predict that. Okay. Now, entropy always drives mixing. So these X's are mole fractions. So let me just grab one of those and say that's the number of moles of 2 over the number of moles total. Okay. And so if you look at this, you have the total moles in the system, and you have the individual partial amounts of moles of all the components. All of these are going to be less than 1, right? Because if you got a mixture, you've got, some fraction of substance A and some fraction of substance B or substance 1 and 2. And so all of these numbers here are less than 1, which means all of the natural logs are negative, less than 0. And so the negative natural logs, we add all of those up, that cancels this negative sign. So the entropy of mixing is always positive. So entropy always wants to mix things, and especially if there's no penalty for mixing. So if there's no penalty for mixing, entropy is going to drive those things. And so just take a mason jar and put, blue M&Ms on the bottom and pick your other color, yellow M&Ms on top, and turn that jar once. What happens? They mix. There's no energetic penalty for mixing, and that's exactly what's happening here. You put all your molecules in one side of the beaker and the other molecules in the other side of the beaker and give it a few milliseconds, and they're mixing. Especially if those molecules are very similar to each other, okay? If they're dissimilar, then one set of molecules may exclude the others. Like water is a total snob, okay? Water likes itself. You put oil and water gets together with water and says, hey, we're polar, let's get together. Hey, hydrogen bonding, okay, I like you guys. And oil, water's like, I don't care about you. You don't hydrogen bond with me, you're not polar. So water excludes the oil. That's why oil and water don't mix. It's the intermolecular forces. Entropy would drive them together, but because of the intermolecular forces, water likes water more than it likes oil. Oil doesn't really care for oil. It's just dispersion forces, very small intermolecular forces. So it's really the water that's excluding the oil. And you think about it, if oil moves out of the way, water clicks. And then to get it back apart, you have to break those cliques. You have to break the polar forces and the hydrogen bonding forces. So how are you going to insert an oil molecule between two water molecules? It takes energy to do that. That's what we're talking about, enthalpy of mixing. Now, entropy wants to drive those things together. So temperature effects can play a role. So if we raise the temperature, then we favor the entropy piece. So if someone tells me oil and water don't mix, I'll smile and say, at what temperature? Because if I raise the temperature enough, then water is so agitated it can't form hydrogen bonding and polar forces for very long. And it's bouncing all over the place, and oil has a chance to mix in because of entropy. Okay. And so this is our, if enthalpy is 0 for ideal solutions, then it's just that entropy of mixing that drives the Gibbs energy. So. Okay, so that's the thermodynamics behind mixing. Now we'll make these mixtures. Again, we're in this particular set of notes, all of these mixtures are miscible. So they mix completely at all proportions. So we have a smooth composition curve from a mole fraction of 0 to 1, and we have, it mixes in all compositions. We will get to phase separation later. Okay. So for ideal solutions, mixing is always spontaneous. Okay, so then this is just sort of one of the foundational principles for equilibrium. So if we have gaseous molecules and liquid molecules and they're mixed together, at equilibrium, the chemical potentials are equal. And so this is even true for non-ideal solutions. So I'm not really going to do much with this, but just this is one of the chemical principles. When spontaneously mixing, vapor and liquid come to equilibrium pretty quickly, actually. And well, I guess it depends on whether the substances are mobile or not. So, and then here's some essential terms. So I'm trying to be very explicit. Like the last slide was sort of background foundational principles, but this slide you have to actually memorize. Okay, so when we use X, we're talking about the liquid phase. So XA is used to designate the mole fraction of A in the liquid phase. So when I talk about mole fraction, it's number of moles of A over number of moles total. If we're just talking about A and B, then it would be NA over NA plus NB. So very straightforward. Then we'll have, in this specifically in this set of notes, Y. YA is designating the mole fraction in the gas phase. So we are dealing with mixtures in the liquid phase and their vapor pressures. So we're in equilibrium with the gas. And then ZA is used to designate the overall mole fraction of A in the vessel. So there'll be some moles of A in the gas, some moles of A in the liquid, some moles of B in the gas, moles of B in the liquid. We would maybe have some sort of lever rule to determine how much gas, how much liquid we have, and that added together would give us the Z component. And we'll see an example of that. So just X, Y, and Z. X is liquid, Y is gas, Z is overall in the container. So here's our first PX phase diagram for an ideal solution. So let me walk you through the axes. And now in any of these phase diagrams, always go to the axes first. So this is pressure here, okay, which is pretty straightforward, pressure in the vessel. This is XA, so mole fraction of A. So that means this is pure A. And if A is 0, then that's pure B. Make sense? Piece of cake? Okay. Now, Roult's law is the partial pressure of A. So this little star here means the pressure of pure A. This would be the partial pressure of A. And so this is great. It's just such a simple equation. It's a linear relationship. I take the pure vapor pressure of A, and then I just take the mole fraction. So if I have 60% A, I have 60% of the pure vapor pressure of A. That's great. That's the simple approximation, right? It makes sense. If I have 0 A, then my vapor pressure of A is 0. If I have 100% A, it's the 100% pure A vapor pressure. And what is it in between? Just take the mole fraction. And if it's 30% A, then I have 30% of that vapor pressure. So that's such a straightforward thing. Don't let that be complicated. Roult's law is what else would you do? It's a great guess. Yeah. So if I have 20% A, then maybe I should just take the pure vapor pressure of A at that temperature and multiply it by 0.2. And then I get the vapor pressure of A. So that's Roult's law. So it shouldn't be any, like, if that confuses you, please let me clarify. I'm not trying to shame you and say you shouldn't have a problem with it. I'm trying to say that's a great approximation. Just take the mole fraction times the pure vapor pressure, and you get the partial pressure of that substance. And then likewise, B, what is the mole fraction of B? Well, that one is just 1 minus XA, right? So if XA is 0, then we're at XB is 1 over here. Okay. And so the partial pressure of B is just the mole fraction of B times the pure vapor pressure of B. Okay. And then all solutions. So this is Roult's law is for ideal solutions. All solutions obey Dalton's law. So we'll take the amount of, let's take right here at 25% A. So we have that vapor pressure of A, that vapor pressure of B. You add that. So I'll do, let's do 1, 2, 3. Okay, so we'll say 3 is equal to 1 plus 2. Okay. Right, so we're going here. You just add those together, and we get that third point. So that's Dalton's law. So I'll just put a line up here, Dalton's law. So that's pretty cool. I can predict the total pressure in the vessel if I know the composition of A, and I know that B is 1 minus that. And I know their pure vapor pressures. Where might I get these pure vapor pressures? We just calculated those in the lab, right? Now, those are the results for the PV lab were kind of not that accurate. Okay, so if you're wondering why your delta H of vaporizations are kind of off, that's just because the Maxwell constructions are not the best. Okay, but at least you're modeling the accurate, like the condensation curve and the vapor pressure. But now you should have an idea of the Clausius-Clapeyron equation and how to calculate vapor pressure. So can CCEQ, does that make sense for you guys? The Clausius-Clapeyron equation from lab, Clausius-Clapeyron equation. And so we'll see that in the notes here in a little bit. But that's where we would get these pure vapor pressures. And if we know the compositions for, if we know the pure vapor pressures, then we can calculate all the pressures in the whole composition curve. We can calculate everything on this whole graph if we know those two numbers. And this is all at a temperature. So this particular substance, this particular diagram is at one temperature. And you change the temperature, the vapor pressures change, and all the curves adjust. Okay. Yeah, here's the Clausius-Clapeyron equation. So if I know the enthalpy of vaporization, and I know the boiling point, so that's the boiling point for that liquid. At the normal boiling point, the pressure of the liquid, the vapor pressure is 1 atmosphere. And so here's my pure vapor pressure as a function of temperature. I need to know the boiling point and the enthalpy of vaporization. I can look those two things up, and then I can calculate the pure vapor pressure at any temperature. And so that's what I have here, these curves. The red one's at 270, the yellow one's at 280, the blue one's at 298. Okay, and so then you see how the pressure grows as the temperature goes up. Now there's another equation that you might use. They're called the Antoine equation, and it's just an empirical fit. It has these constants A, B, and C, which you look up, and the CRC will have those. Wikipedia will have those, which if you look at the references for Wikipedia, they're pulling them from the CRC. So if you find the Antoine equations and you pull the thread, you probably get back to the CRC. Okay, so pretty straightforward calculation. You can calculate the vapor pressure. You know, either way, if you have the boiling point and the delta H of vaporization, you could use the Clausius-Clapeyron equation. I like that one actually, but they both work. Now, one thing that's interesting, these px phase diagrams are temperature dependent. And so if we're looking at this, here's 1 atmosphere. And whenever the vapor pressure of the substance, the mixture, equals 1 atmosphere, it's boiling. So this is the boiling point here. Wherever it crosses 1 atmosphere, that's the boiling point. And so this is showing that substance A boils at 270. You see that? So 270 is actually the boiling point for substance A. That's when substance A's pure vapor pressure equals 1 atmosphere. So the solution is boiling here. If at 270 degrees, we would have the boiling point of substance A. If we had this mixture put together, and let's say we mixed together this one here. So we mixed some B in with A. It looks like we're about 60% A and 40% B. If we mix that together, look at B's vapor pressure. It's much lower. And so that means that we have to raise the temperature to get this mixture to boil. So this mixture boils at, 60% A boils, at 280 Kelvin. This was 270 Kelvin. And then if we mix in more B, since B is not very volatile, it's going to raise the boiling point even more. And so here at 298 Kelvin, that mixture where it's about, let's see, looks like 30%, maybe 33% A and 67% B boils at 298. So we should be able to look at this diagram, and this is something that you should be able to recognize instantly. Which of these substances, A or B, has the lowest boiling point? Whichever one has the highest vapor pressure has the lowest boiling point. Because remember, it's boiling when that vapor pressure equals 1 atmosphere. So look at what, here's B. How can I get pure B up to 1 atmosphere? Well, I got to really raise the temperature. So it's the least volatile substance, and so it's going to have the highest boiling point. So the temperatures and pressure curves kind of flip upside down. Like if I'm thinking in temperature, but I'm looking at pressure, the highest pressure substance is going to be the lowest boiling point. Now let's look at the vapor composition line. This one has a tendency to break people's brains, okay? The compositions of the liquid phase and the vapor phase are not the same. And that's a good thing. Otherwise, we could never use distillation to separate substances because the vapor phase has a different composition than the liquid phase. That allows us to separate things with distillation. So here we have this map of pressures and compositions of which each phase is stable. And so if we're looking at this, we see this is the high pressure side. So this is going to be the liquid line. This is the low pressure side. This is going to be the gas line. So we have these two composition lines. And so that's what we're saying, the pressure total versus XA, the pressure total versus YA. And so if we're boiling this substance, so we have this mixture and it's boiling, so it's right here. So we have this in the pot. So we have this mixture of 33% A in the pot and 67% B, and we warm it up. We warm it up to whatever temperature this diagram is made at, and it starts to boil here. And if we were to zoom in, why did that line disappear? That's weird. Okay. If we were to then grab the gas out of that and analyze it, it would have this composition, because that's the composition of the vapor. So it's really strange. This is the liquid composition, but coming out of the surface of that liquid, what do you think is going to be preferentially coming out of the surface of the liquid? The more volatile substance. And so since A is more volatile than B, it's enriched. So we have more A in the vapor than we have in the liquid. That makes sense. A is more volatile. So it's going to come out of the surface of the liquid more than B does. Now, if we were to just do a simple distillation, we would have one step, and that would be the composition in our simple distillation flask. So we get like a really low, like just have the pot with the mixture in it, and then you go right into the condenser, into another thing. So no fractioning column. Just warm it up, single step, condense the vapor. That's how much enrichment we would have in A. So a single step distillation would just give us that much enrichment. But hey, it's nothing, not nothing. It's 50% A now instead of 30% A. So that's pretty good. If we wanted to do this over and over again, we could create a tall column where it would condense, and then before it gets back down, it would re-evaporate and condense and re-evaporate. And this fractional distillation goes through multiple little boiling points and condensations. And then finally pure A comes out the top. Yeah. So this is just showing you what I kind of drew by hand. You know, if we boil the liquid, then we take that pressure line straight across and we hit the gas phase, and YA would be what's condensed in a simple distillation. Now here's this curve, this P partial pressure of A over total pressure. And so the total pressure is just a linear interpolation starting at the pressure of B down here, plus this difference in the partial pressures of A and B times XA. And so the bigger this difference here, the more these lines are separated. Okay, so we want a very big difference in the volatility of our substance if we want good separation. Now this is pressures, right? When we get to temperatures, that would be a big difference in the boiling points of those substances. And so that's the easiest thing to do in separations, is if your substances that are mixed together have dramatically different boiling points, then it's easy to separate them by distillation. And what we're seeing in the pressure curve, that means they have dramatically different vapor pressures, which makes sense. If I have A is super volatile and B is not, so I've got, say, hexane. Well, let's take a candle, for instance. Okay, I've got a molten candle, and that oil, the heavy long molecules of wax, are not very volatile, but the vanilla compound in there is, and so it's going to come out with a much more volatile exit of that surface of that liquid, and so then you'll fill the room with nice, wonderful vanilla smell instead of the hot waxy smell. You still get a hot waxy smell, right? But not very much. And it's not very strong in your nose. It's a good thing too, because the candles would drive us out of the house if we were real sensitive to the waxy smell. Okay, now let's look at dissimilar liquids. Look how strange those curves are. Pretty ugly, yes? Okay. So there are substantial deviations from the ideal partial pressures. And this is acetone and carbon disulfide. So if you think about the intimate contact that these molecules have in the liquid phase, they can dramatically change the volatility of those molecules if they interact. And so in this situation, we have acetone, which hydrogen kind of doesn't really hydrogen bond with itself, but there's definitely a polarity associated with acetone. And so we can have acetone molecules lining up, snapping together with their polar forces and forcing carbon disulfide, which is kind of like CO2, but with S's instead of oxygens. Okay, a nonpolar molecule not really interested in acetone. And so we mix these together and they kind of hate each other. And so if I have a lot of acetone and a little carbon disulfide, then the carbon disulfide comes out of solution. So over here, this is mole fraction of carbon disulfide. So I have mostly acetone, a little bit of carbon disulfide, and the carbon disulfide's partial pressure is way above what I would expect from Roult's law. So remember, these curves are Roult's law. These are experimental curves. The blue are experimental curves. So that's strange. I put, say, 10% carbon disulfide in the solution with acetone, and I expect 10% of the vapor pressure of carbon disulfide, but it's more like 30%. So I'm off by 200%. It's got 3 times the vapor pressure I expect. That's crazy. It's because it just hates acetone. Okay. And then here, if I have mostly carbon disulfide and I have a little bit of acetone in there, it also comes out preferentially. And the acetone is just not happy in that much carbon disulfide. And so it just comes out. Once it leaves the solution, why would it ever go back? There's nothing down in that solution for the acetone to bond with or associate with. You add these two effects together and you get a dramatically large total pressure with a maximum somewhere around here of like 67% carbon disulfide. So that's pretty bizarre. If I were to draw Dalton's law here, this would be the predicted pressure of all mixtures, right? And so I predict it to have a pressure of, say, close to 300 torr, and I'm getting 450. So that's a big error. So this would be a non-ideal solution, and these would be solutions that hate each other. Okay. And so they have a lot of time to interact in the liquid phase. They have a lot of time to repel each other if they don't like each other. If they do like each other, they may suck everything into solution and really lower the vapor pressure. So you could have a curve that deviates below expected if they like each other. So let's do a top hat. So in this pressure composition phase diagram, so Px is pressure composition, so the X is composition. Which substance has the lowest boiling point? There's a timer on this one, so try to answer quickly but correctly. Do you need to log in still? Okay, I'll extend it at 15 seconds. You're not in yet? Okay, keep trying.
It won't load at all.
So you're logged into Top Hat, but it's not loading?
No, the website won't give me access to it. I think it's the school Wi-Fi. School Wi-Fi is always fast.
Well, I want you to try. Is it... Okay. Yeah, PA. Very good.
Answer verbally.
All right, so we got a pretty, that's kind of funny that the split was the actual, oh no, never mind. I don't want to say anything. Yeah, so it's substance A. Substance A is the highest vapor pressure, okay? All right. Because it's more volatile, then it's going to boil at a lower temperature. Okay, so, all right, so let's do the next problem. In this PX phase diagram, which composition has the lowest boiling point? So we're looking at this crazy composition over here. So we have lots of options. Which composition, and you could think of pure substance in the PX curve as a composition. It's just 100% of one thing or 100% of the other. That's also a composition. Yeah, go ahead. Choices are down here, so 4 choices. And the x-axis is mole fraction of carbon disulfide. does this guy do? Oh, is that okay? No, it's probably not okay. Too small. Oh, oh you can? Okay. All right. One more person. All right, good. Okay, let's see what the class thinks. All right, 100% CS2, 67% CS2. So nobody likes acetone. That's good. It's not acetone. Yeah. So we're looking at here. Here's the vapor pressure of pure acetone over here where my little mouse is. Okay. And this is the vapor pressure of pure carbon disulfide. So those are the both endpoints. Okay. And certainly carbon disulfide has a higher vapor pressure, so it would boil at a lower temperature. Okay. But look here in this mixture, right there, that has the highest vapor pressure. So that composition would be the earliest boiling, the lowest boiling point. And so 67% roughly. So 2/3 carbon disulfide would have the highest vapor pressure. So that mixture would have the lowest boiling point. Okay. So that tells we need to work on reading the diagrams. Yeah. So that's the thing that this set of this part of the course is really focused on reading these diagrams and understanding what they're telling us. Okay, because you can find these diagrams for all the different substances that you deal with, and when you're making mixtures, and so being able to read them is a skill that's worthwhile. Now, how do we deal with this non-ideal solution? We have a different law, Henry's law. Okay, so we focus on the limits. If we're dilute solutions of B, they're dominated by the individual particles of B. So down here we're at dilute B. So dilute solutions of B are down here. Okay. And that's B has already been separated from other B's. It's dilute, so it's individual molecules of B inside this other solvent that it may or may not like. And if it doesn't like it, that B is going to leave. And so you have a higher vapor pressure than you expect on the dilute side, or lower. If it does like that solvent, it's going to stick in that solvent better than it would itself. Okay. But then on the concentrated side, so this is all pure B, almost pure B, or I would say dirty B, right? It's concentrated solution of B. And it's going to behave like B in B. So it's going to be very similar to the pure vapor pressure, which would be dominated by Roult's law. And so those are the limits. And then this thing in between just connects the two. So this equation here is pretty complicated, but that's the behavior of a non-ideal solution. It sort of comes in like a landing plane on Roult's law here. So see how it kind of approaches gradually, and then it lands on the little runway there. So that's how it behaves up here at the concentrated side. It obeys Roult's law. And then down here, it's taking off on this trajectory like Henry's law. And so we have this Henry's law constant and the pure vapor pressure. So this Henry's law, the partial pressure of the solute depends linearly upon the mole fraction of the solute, but the proportionality is not the vapor pressure. So it's aiming at a point that's not P star. So if B is the solvent, it's Roult's law, but if B is the solute, we have Henry's law. So, it's linear for a little bit, right? So it's linear for that range there, and the proportionality is KB. So it's the same kind of equation. You see, instead of P star, we have KB. We have this Henry's law constant. And that would be what you would use for the solute. If B is the solute, you use the Henry's law constant for B in A. So this is the constant for B in A. So this is a really nightmare for a table, because this might be, you have for every mixture, let's say you look up a Henry's law constant for all these substances in water. So you have a different constant for every substance. You have a Henry's law constant for acetone in water, for chloroform in water, for ethanol in water. So it's there's really no general trend like Henry's law constant for organic ketones or something like that. No, every individual substance has a different sort of association with water or with some other substance. So every binary mixture has a different set of Henry law constants for every compound. And whether it's this, if it's the solute, then you have a Henry's law constant. If it's the solvent, you just use the mole fraction and the pure vapor pressure. So Roult's law is easy. You can look up the vapor pressure with the Clausius-Clapeyron equation. You know the mole fraction. So like if it's 0.9, if it's 90% B, then you would calculate the vapor pressure of B as 90% of the vapor pressure. Okay. But if it's 10% A or what have you, then you need the Henry's law constant. And then if it's ideal, then the Henry's law constant is equal to the vapor pressure. So the closer KB is to P star, the more ideal the mixture. The further away KB is from P star, the more non-ideal the mixture. So it's like who was it, Dickens, A Tale of Two Cities? A Tale of Two Mixtures. So we have on the left the acetone and carbon disulfide who hate each other, not friends, right? Not BFF. Okay. But chloroform and acetone, hey, they're great. Okay. Just notice how the Roult's law lines here, these lines are all underneath those. And then the total is underneath that. So when I mix chloroform and acetone at the optimum amount right here, then I expect a vapor pressure of 300 torr and the vapor pressure is 250, which is strange, right? It should be 300 torr because I've got this mole fraction of acetone, that mole fraction of chloroform. I use Roult's law and add them together to get the Dalton's law, the total pressure in the container, and it's much less than that. And it's much less than that because chloroform and acetone can hydrogen bond. So you have that chloroform. I'm just going to put methyls on there. Okay. So you have this hydrogen bonding, so they can actually associate with each other. And so then because there's this hydrogen bonding that doesn't really exist when they're by themselves, the mixture is lower energy, more stable, has a lower vapor pressure than any of the pure substances. So that's where you're using intermolecular attractions to your advantage if you want something that has a low vapor pressure. Okay. So low vapor pressure would mean a higher boiling point, right? So this one had a really low boiling point. Over here, which substance or composition would have the lowest boiling point? It would be acetone. This is the highest vapor pressure. Pure acetone will have the lowest boiling point. Then pure chloroform. Then this mixture. This mixture would have the highest boiling point because that's the lowest vapor pressure. So you're getting better at, you got a low vapor pressure, it's a high boiling point. Got a high vapor pressure, it's a low boiling point. So just being able to think through those things in your mind, that's a skill that I'm trying to develop in you today. Then there's just some more supplemental stuff. We talk about activity coefficients, and this is experimental data, and so you have essentially this activity coefficient that corrects your mole fraction and gives you these curves. Now you can model that with this thing called the Margulese equation, and it can give you those strange shapes. And then we'll talk about this some more later. All right, so we're pretty much out of time. And that's your PX phase diagram. So the screws are tightening a little bit, and it's getting more complicated. But next time, after spring break, is really fun because we switch to a temperature composition phase diagram. And then we really get into distillation and fractional distillation and theoretical plates and all of that for separations. So it's the science behind separations next time. All right. Have a safe break.